Tonight, we're taking a gentle journey into one of humanity's most curious hypothetical questions. What would actually happen if we gathered every nuclear weapon on Earth into one enormous pile and set them all off at once? It's the sort of question that sounds dramatic, but when you break it down with physics and patience, it becomes a quietly fascinating exploration of energy, scale, and our planet's remarkable resilience. Before we begin tonight's journey, feel free to share what time it is and where you're listening from. It's always wonderful to know where these quiet little thought experiments are floating off to. So settle in, close your eyes if you like, and let's take a slow, thoughtful wander through one of science's more explosive questions. After all, sometimes the most peaceful way to understand power is to imagine it safely contained in the realm of pure theory. 15,000 sounds like a lot until you realize we're talking about weapons that could reshape continents. That's how many nuclear weapons currently exist on our planet, scattered across silos and submarines, quietly waiting in storage facilities around the world. It's a number that feels both enormous and surprisingly modest, depending on how you look at it. The United States and Russia each keep about 7,000 of these devices, while the remaining 1,000 or so are distributed among France, China, the United Kingdom, Pakistan, India, Israel, and North Korea. Each country has its own reasons, its own history, its own careful calculations about safety and deterrence. But tonight, we're not here to debate policy or politics. We're here to explore what all that accumulated energy might do if it were gathered in one place. To put this in perspective, imagine trying to destroy every city on Earth. There are roughly 4,500 cities with at least 100,000 people living in them. Some are sprawling metropolises, others are modest urban centers, but let's say, on average, it would take about 3 nuclear weapons to completely level each one. By that calculation, our current global arsenal could erase every single city on the planet, killing roughly half of humanity in an instant, and we'd still have 1,500 weapons left over. That's what experts might politely call overkill, though the word feels almost quaint when you're talking about such scales of destruction. It's like having enough flour to bake bread for a village when you only need a single loaf. Except, of course, the mathematics of devastation don't quite work like baking. Each individual warhead is, in its own way, a marvel of engineering. A typical modern weapon contains the explosive equivalent of 200,000 tons of traditional explosives. That's enough energy to power a small city for months, compressed into a device you could fit in the back of a truck. The engineering required to achieve this level of energy density is genuinely remarkable, even if the purpose is troubling. If you were to line up 200,000 tons of conventional explosives, the pile would stretch for miles. It would take months to manufacture and an army to transport. But nuclear weapons achieve the same effect through the simple act of convincing atoms to break apart or stick together, releasing the energy that normally holds matter itself in place. It's almost elegant in a deeply unsettling way. The physics behind it all comes down to Einstein's famous equation: energy equals mass times the speed of light squared. What this means, practically speaking, is that even tiny amounts of matter contain staggering quantities of energy. When you convince a small amount of uranium or plutonium to undergo fission, or when you force hydrogen atoms to fuse together, you're essentially converting a bit of mass directly into energy. Not much mass, mind you, perhaps just a few grams. But the speed of light is an enormous number, and when you square it, the result is almost incomprehensible. This is why nuclear weapons can be so compact, yet so powerful. They're not really explosives in the traditional sense. They're matter conversion devices, tiny machines that transform substance into pure energy. It's the same process that powers the sun, just engineered to happen very quickly in a very small space. But what's particularly interesting about our global nuclear arsenal is how it reflects human psychology as much as human physics. We've built enough destructive power to end civilization several times over, not because we need that much, but because uncertainty and fear drive us to accumulate more than logic would suggest necessary. It's like keeping a dozen umbrellas by the door just in case it rains really, really hard. And yet, for all their destructive potential, these weapons mostly just sit quietly in their storage facilities, slowly aging, requiring maintenance, gradually becoming obsolete as newer technologies emerge. In many ways, they're less like active threats and more like sleeping giants, vast concentrations of energy waiting patiently in the dark. Scientists who study these things often speak about nuclear weapons in terms of yields and megatons, clinical terms that make the mathematics feel less overwhelming. But every now and then, it's worth stepping back and marveling at what we've actually accomplished. Humans, these curious, creative, occasionally problematic creatures, have learned to bottle starlight and store it in underground silos. We've captured the fundamental forces that shape the universe and made them portable. Whether that represents the pinnacle of human ingenuity or its greatest folly depends largely on your perspective. But as we drift towards sleep tonight, perhaps we can appreciate it simply as an extraordinary example of what happens when curiosity meets engineering, even when the results are more powerful than we quite know what to do with. The real question, of course, is what would happen if all that carefully stored energy were released at once? And that's where our gentle thought experiment begins. Picture, if you will, the world's most dangerous warehouse. Not particularly large, perhaps the size of a modest shopping center, but containing within its walls the combined nuclear arsenal of humanity. 15,000 warheads, stacked somewhat haphazardly like the universe's most concerning Lego collection. This is where our thought experiment begins, in the heart of the Amazon rainforest, where thick green canopy stretches to every horizon. We've chosen the Amazon not out of any ill will toward trees, but simply because it's one of the most remote places on Earth, far from major population centers. If we're going to conduct an experiment with the energy equivalent of 3 billion tons of conventional explosives, it seems polite to do it somewhere that won't immediately bother the neighbors. 3 billion tons is a number that slides past the mind without leaving much of an impression. It's simply too large to feel real. But here's one way to think about it. Imagine taking the entire island of Manhattan, every building, every street, every hot dog cart and subway tunnel, and rebuilding it entirely out of explosives, stacked as high as the tallest skyscrapers. That's roughly the amount of destructive power we're talking about. Or, if you prefer a more natural comparison, consider volcanoes. Throughout recorded history, one of the most devastating volcanic eruptions occurred in 1883 on the island of Krakatoa. The explosion was so powerful that it destroyed 70% of the island itself, along with much of the surrounding archipelago. The sound of the eruption traveled around the world multiple times, a pressure wave that circled the globe for days. Tens of thousands of people perished, and the effects were felt worldwide for months afterward. Our hypothetical nuclear pile contains 15 times more energy than that legendary eruption. 15 Krakatoas, all compressed into a space you could walk across in a few minutes. It's a sobering thought, though from the perspective of planetary physics, it's still quite small. The Earth has survived much worse, including the asteroid impact that ended the age of the dinosaurs, which released thousands of times more energy than our entire nuclear arsenal. But scale is a relative thing. While our pile might be modest from a geological perspective, it would certainly be noticeable to anyone living on the surface at the time. The Amazon rainforest, with its thousands of species of birds, millions of insects, and vast networks of trees that have been quietly growing for decades, is about to have a very unusual day. Standing at a safe distance, if such a thing were possible, you might notice how ordinary everything looks in the moments before ignition. The warehouse sits there peacefully among the trees, giving no indication that it contains enough energy to briefly outshine the sun. Birds call from the canopy, insects buzz through the humid air, and somewhere in the distance, a river murmurs its way toward the sea. The actual process of detonation would be almost disappointingly simple. Nuclear weapons are designed to trigger each other, so once the first device activates, the rest would follow in a cascade lasting perhaps a few seconds. Each weapon would add its energy to the growing fireball, like throwing logs onto a fire that's already large enough to be seen from space. The moment of ignition itself would be nearly instantaneous. 1 second, there's a warehouse full of metal and explosives sitting quietly in the forest. The next second, there's a growing sphere of plasma expanding at several thousand miles per hour, converting everything it touches into more plasma. Trees, soil, rocks, water, and quite possibly a few startled parrots, all transformed into the fundamental particles that make up very hot, very energetic matter. What's remarkable about nuclear explosions is how they briefly recreate the conditions found inside stars. For a few moments, there in the heart of the Amazon, temperatures would reach tens of millions of degrees, similar to the core of the sun. Pressures would be enormous, beyond anything normally found on Earth's surface. It would be a tiny piece of stellar physics, transplanted temporarily to our quiet planet. The light from this event would be visible from extraordinary distances. People in neighboring countries might mistake it for a second sunrise, appearing suddenly in the wrong direction. Satellites in orbit would register the flash, and sensitive instruments around the world would begin detecting the first signs that something very unusual had just occurred in South America. But the light would be just the beginning. Light travels at the speed of light, naturally enough, so it reaches distant observers first. Sound travels much more slowly, and the pressure wave from an explosion this size would take considerably longer to make its journey around the world. The shock wave from Krakatoa circled the globe several times. Our explosion would do the same, but with significantly more enthusiasm. All of this would unfold with a kind of terrible beauty. Destruction on this scale operates according to the same physical laws that create stars and shape galaxies. It's the same nuclear physics that powers the sun and every other star in the night sky, just concentrated into a much smaller space and time. In a strange way, it's one of the most natural things in the universe. Matter converting itself into energy, following the fundamental equations that govern everything from atoms to solar systems. And so, in our quiet thought experiment, we watch as 15,000 carefully engineered devices fulfill their purpose all at once, turning a small patch of rainforest into a brief, brilliant demonstration of how the universe works when you convince it to release its hidden energy very quickly. In the first second, silence ends and physics takes over. What happens next unfolds with the terrible precision of natural law, each moment following inevitably from the last, like a stone dropped into still water, creating ripples that spread far beyond where it fell. The fireball begins as a point of light brighter than the sun, then expands outward at several miles per second. Within moments, it grows to 50 kilometers across, a sphere of superheated plasma that vaporizes everything within its reach. 50 kilometers is roughly the distance between neighboring cities, so if you place this event in familiar surroundings, the fireball alone would stretch from downtown to the suburbs and beyond. Everything within this sphere simply ceases to exist in any recognizable form. Trees that have grown for decades, rocks that have sat peacefully for millions of years, rivers that have carved their paths through the landscape over geological time, all become part of the expanding ball of energy. It's not burning, exactly, which implies that something remains to burn. It's more complete than that. Matter converting directly to plasma, atoms stripped of their electrons, the basic building blocks of the physical world temporarily reorganized into something much simpler and much hotter. But the fireball is just the beginning. Behind it comes the blast wave, a wall of compressed air moving outward at tremendous speed. This pressure wave flattens 3,000 square kilometers of forest, an area roughly the size of Rhode Island. Trees that survived centuries of storms, droughts, and floods are knocked over like grass in a hurricane, their trunks snapping with sounds like thunder if anyone were around to hear them. The Amazon rainforest is home to an estimated 10% of all known species on Earth. In these few moments, countless creatures experience the end of their evolutionary journey, not through gradual climate change or habitat loss, but through a sudden transformation of their environment into something completely inhospitable to life. It's a sobering reminder that for all the complexity and beauty of biological systems, they remain fundamentally dependent on relatively stable physical conditions. At distances of up to 250 kilometers from the blast, everything begins to burn. This isn't the blast wave anymore, which has long since passed, but something more insidious, thermal radiation. The fireball emits energy across the entire electromagnetic spectrum, including massive amounts of infrared radiation, which we experience as heat. At this distance, the heat flash is intense enough to ignite anything flammable, turning a vast region of the Amazon into a spontaneous wildfire. Picture the scene from high above if you could somehow observe safely from orbit. A perfect circle of absolute destruction at the center, surrounded by a much larger circle where fires spring up as if lit by an invisible hand. Beyond that, trees still stand, but they lean away from the blast center, their leaves scattered by winds that arrived ahead of the main shock wave. The sound of the explosion travels outward more slowly than light, or the initial pressure wave, but when it arrives, it's unlike anything heard in the modern world. The explosion of Krakatoa was audible 3,000 miles away, and our event is 15 times more powerful. The sound would circle the Earth tens of times over the coming weeks, a deep, rumbling reminder that something extraordinary had occurred. Meanwhile, upward, the mushroom cloud begins its journey towards space. This iconic shape forms because hot gases rise rapidly, creating a column of ascending material that spreads out when it reaches the limits of the atmosphere. But this mushroom cloud is unlike anything previously seen. It pushes upward with such force that it reaches the stratosphere, that high, stable layer of atmosphere where commercial aircraft fly. It might even brush against the edge of space itself, creating a temporary bridge between the Earth's surface and the cosmic void above. Millions of tons of material are hurled into the sky: soil, vaporized trees, bits of rock, and countless particles too small to see. Much of this material has been irradiated by the nuclear explosion, transformed into radioactive isotopes that will slowly decay over years, decades, or centuries. This contaminated dust rides the mushroom cloud high into the atmosphere, where winds will carry it around the globe. From a physics perspective, what's happening is a massive transfer of energy from a concentrated source into the surrounding environment. The nuclear explosion converts matter into energy, which then pushes against everything nearby, accelerating gases, heating surfaces, and setting objects in motion. It's the same principle that makes a firecracker pop, just scaled up by a factor of several billion. But there's something almost serene about observing this from a distance, thinking about it in terms of natural processes. The explosion follows the same conservation laws that govern every other physical interaction. Energy cannot be created or destroyed, only transformed from one form to another. In this case, the binding energy that held atomic nuclei together is being converted into kinetic energy, thermal energy, and electromagnetic radiation. It's textbook physics, just with unusually dramatic visual effects. As the initial explosion subsides and the fireball begins to cool, the immediate effects start to fade. The blast wave continues outward, growing weaker with distance until it becomes merely a strong wind, then a gentle breeze, then nothing more than a slight disturbance in air pressure detectable only by sensitive instruments thousands of miles away. But while the immediate explosion may be over, its consequences are just beginning. The smoke and dust thrown into the atmosphere will affect weather patterns. The radioactive material will slowly settle back to Earth. The fires will burn for weeks or months. And somewhere in laboratories around the world, seismographs will have recorded the event, scientists will begin analyzing data, and the slow process of understanding what just happened will begin. For now, though, there's just the quiet aftermath. A small crater in the Brazilian rainforest, still glowing softly with residual heat, surrounded by a landscape transformed. Smoke has a way of telling stories, and this smoke has quite a tale to share. High above the Amazon, the mushroom cloud continues its slow journey upward, carrying with it the remains of what was once a thriving ecosystem. But this isn't ordinary smoke from a campfire or even a forest fire. This is matter that has been fundamentally changed, atoms that have been split and rearranged, particles that now glow with invisible energy. The mushroom cloud reaches heights that commercial aircraft never see, pushing into the stratosphere with such force that it creates its own weather system. At these altitudes, the air is thin and cold, and the normal patterns of wind and circulation that govern our daily weather don't quite apply. Instead, the cloud begins to spread out horizontally, like water poured onto a flat surface, creating a vast, circular shadow that can be seen from space. Within this cloud, millions of tons of debris drift on currents of superheated air. Some of it is simply dirt and rock, pulverized by the blast and thrown skyward. But much of it is more exotic, radioactive isotopes created by the nuclear reaction itself, elements that don't normally exist in nature, atoms that are slowly falling apart and releasing energy as they decay. Radioactivity, despite its fearsome reputation, is actually a fairly gentle process on the atomic scale. Individual atoms simply become unstable and emit particles as they transform into more stable forms. It's like a tiny firework going off inside each unstable nucleus, invisible to the naked eye but detectable by instruments. The problem arises when you have trillions upon trillions of these tiny fireworks scattered across the landscape. As the radioactive particles in the mushroom cloud begin to settle back toward Earth, they'll be distributed by wind patterns across a vast area. The amount of radioactive material in the global environment will roughly double, which sounds alarming until you remember that radioactivity is already all around us. The rocks beneath our feet, the air we breathe, even our own bodies contain naturally occurring radioactive elements. What we're adding is a temporary spike, unpleasant and dangerous, but not necessarily civilization ending. Still, there will be consequences. A large area around the blast site will become uninhabitable for years or decades, not because of the initial explosion, but because of the lingering radiation. Plants and animals that survive the immediate effects will face increased cancer rates. Human settlements hundreds of kilometers downwind will need to be evacuated or extensively decontaminated. But perhaps the most fascinating consequence isn't what falls back down, but what stays up. Some of the particles launched by our explosion will be carried to the very edge of space, high enough to be influenced by solar radiation and magnetic fields. These particles will drift slowly around the globe, taking years to settle, creating a thin, radioactive haze that wraps around the entire planet. This global distribution of particles will have subtle but measurable effects on climate. The tiny particles act as nucleation sites for cloud formation, potentially increasing cloud cover. They also absorb and scatter sunlight, reducing the amount of solar energy that reaches the Earth's surface. The result is a phenomenon that scientists call nuclear winter, though in this case, it might be more accurate to call it nuclear autumn. Global temperatures might drop by a few degrees for several years. That doesn't sound like much, but it's enough to affect growing seasons, shift weather patterns, and stress ecosystems that are already struggling with the direct effects of radioactive fallout. Forests that survived the initial blast might find themselves dealing with shortened summers and longer winters. Rivers might freeze earlier and thaw later. Migratory animals might find their traditional routes disrupted by changes in seasonal timing. From an atmospheric physics perspective, what's happening is a temporary perturbation in the Earth's energy balance. The planet receives energy from the sun and radiates it back into space, maintaining a delicate equilibrium that keeps surface temperatures within the narrow range where liquid water can exist. Our explosion has temporarily shifted that balance by adding particles to the atmosphere that interfere with both incoming and outgoing radiation. It's worth noting that the Earth has experienced much more dramatic climate shifts in the past. Ice ages, volcanic winters, asteroid impacts, and massive volcanic eruptions have all caused far more severe disruptions to global climate. Our nuclear explosion, for all its local devastation, is still a relatively minor event from the planet's perspective. The climate effects will be noticeable but temporary, lasting perhaps a few years before the atmosphere clears and normal patterns resume. Meanwhile, life continues its ancient work of adaptation and recovery. The Amazon rainforest, despite losing a significant portion of its area, still contains vast regions that were untouched by the blast. Seeds blown in from unaffected areas will begin sprouting in the contaminated soil. Plants have a remarkable ability to absorb and concentrate radioactive elements, gradually cleaning the environment as they grow and die. Animals, too, will begin returning to the affected areas, though they may carry radioactive isotopes in their bodies for generations. In a strange way, the exclusion zone around our blast site might become a wildlife refuge, free from human development and hunting, where nature can slowly reclaim the damaged landscape. Scientists studying the aftermath will discover that life is remarkably resilient. Bacteria and fungi, already abundant in rainforest soil, will continue their work of decomposition and nutrient cycling. Some species will actually thrive in the changed environment, filling ecological niches left vacant by more sensitive species. And high above it all, the last traces of our mushroom cloud continue their slow journey around the globe, a faint reminder of what happens when humanity's most powerful technologies are released all at once. The particles will eventually settle, the radiation will decay, and the climate will stabilize. But for now, the sky itself carries the memory of our hypothetical moment, written in isotopes and scattered on the wind. Fire, it turns out, is an excellent traveler, and today it has quite a journey ahead. What began as thermal radiation from our explosion has now become something much more persistent and far-reaching. Massive wildfires that spread outward from the blast site like ripples on a pond, except these ripples burn everything they touch. The Amazon rainforest, for all its lushness and humidity, burns more easily than you might expect during dry seasons. But these aren't ordinary fires started by lightning or human carelessness. These are fires ignited simultaneously across thousands of square kilometers by the intense heat flash of our nuclear explosion. It's as if someone had lit a match the size of a small country. Wildfire behavior follows its own peculiar physics. Fire needs three things: fuel, oxygen, and heat. In the Amazon, fuel is abundant in the form of dense vegetation that has been accumulating for decades. Oxygen is plentiful in the atmosphere, and our explosion has provided more than enough heat to get things started. Once ignited, the fires create their own weather systems, generating winds that spread flames even faster while creating updrafts that launch burning debris far ahead of the main fire line. These fire-generated winds can reach hurricane force, turning the normal progression of flames into something much more chaotic and unpredictable. Burning leaves and branches are lifted high into the air and carried for miles before falling to earth, starting new fires far from the original blaze. It's a process called spotting, and it allows wildfires to jump rivers, roads, and other barriers that might otherwise contain them. As the fires spread, they begin to affect weather patterns across South America. The massive amounts of smoke and ash being pumped into the atmosphere create local changes in temperature and humidity. Cloud formation is disrupted. Rain patterns shift. What started as a localized event begins to influence weather systems across the entire continent. The smoke itself becomes a character in this story. Unlike the radioactive particles from the mushroom cloud, which are invisible and detectable only by instruments, the smoke from burning forests is very much visible. Thick, dark columns rise from the fire zones, merging into vast clouds that can be seen from satellites in space. These smoke plumes stretch for hundreds of miles, casting shadows over regions that are themselves hundreds of miles from the nearest flame. For wildlife, the spreading fires represent an almost incomprehensible catastrophe. Animals that might normally escape a localized wildfire by moving to unburned areas find themselves surrounded by flames on all sides. Birds, being mobile, have the best chance of escaping, but even they face challenges when the air itself becomes difficult to breathe. Ground-dwelling animals face even greater difficulties, particularly those with limited mobility or specific habitat requirements. But perhaps most significantly, the fires begin to release truly enormous quantities of carbon dioxide into the atmosphere. The Amazon rainforest is sometimes called the lungs of the earth because of its role in absorbing carbon dioxide and producing oxygen through photosynthesis. When you burn a forest, you reverse that process. All the carbon that was slowly absorbed and stored in trees over decades gets released back into the atmosphere in a matter of weeks. The carbon release from our fire would be equivalent to several years' worth of global fossil fuel emissions, all released in a compressed time frame. This represents a significant pulse of greenhouse gases entering the atmosphere, which will contribute to global warming for decades to come. It's one of those feedback effects that make large-scale environmental disasters particularly concerning. The initial event triggers secondary effects that continue long after the original cause has passed. From a chemistry perspective, what's happening is a massive oxidation reaction. The complex organic molecules that make up wood, leaves, and other plant material are combining with oxygen from the atmosphere, releasing energy in the form of heat and light, while producing carbon dioxide and water vapor as byproducts. It's the same basic reaction that happens in a fireplace or a car engine, just scaled up by a factor of millions. The fires also release other compounds into the atmosphere: nitrogen oxides, volatile organic compounds, and particulate matter that affects air quality across a vast region. Cities thousands of miles from the fire zone experience hazy skies and reduced visibility. People with respiratory conditions find themselves struggling to breathe, even in areas where no flames are visible. As the fires continue to spread, they begin to affect human settlements as well. Towns and cities in their path face impossible choices: evacuate and hope there's somewhere safe to go, or stay and try to defend their homes against a wall of flames that might be hundreds of miles wide. Roads become choked with smoke, making evacuation difficult even for those who choose to leave. But fires, like all natural phenomena, eventually run out of fuel or encounter conditions that prevent their spread. Rainfall, rivers, areas of sparse vegetation, or simple exhaustion of available fuel all serve to limit how far the flames can travel. What starts as a seemingly unstoppable force gradually breaks up into smaller, more manageable blazes that can be fought with conventional firefighting methods. The aftermath reveals a transformed landscape. Where dense rainforest once stood, there are now vast areas of charred ground dotted with the blackened stumps of what were once towering trees. The soil, stripped of its protective cover of vegetation, becomes vulnerable to erosion. Without root systems to hold it in place, nutrient-rich topsoil washes away with the first heavy rains, creating muddy rivers and changing drainage patterns across the region. Yet even in this devastation, there are signs of resilience. Many rainforest plants have evolved to survive periodic fires, with seeds that actually require heat to germinate or root systems that can regrow from underground storage organs. Within months of the fire's passing, the first green shoots begin appearing among the ash, starting the long process of forest recovery that will continue for decades to come. And so the fires burn themselves out, leaving behind a changed world but not a dead one. Radiation, despite its invisible nature, leaves surprisingly visible consequences. As our hypothetical fires burn themselves out and the immediate devastation settles into a new kind of normal, we're left with perhaps the most persistent and troubling legacy of our thought experiment. Radioactive fallout scattered across a significant portion of South America and, eventually, the globe. Fallout is simply radioactive material that has been lofted into the atmosphere and then falls back down, carried by wind and gravity to locations far from where it originated. It's a rather mundane name for something so consequential, like calling a hurricane some wind or an earthquake, a bit of shaking. But the mundane name reflects an important truth. Fallout follows predictable physical laws and can be understood, measured, and to some extent managed. The radioactive isotopes created by our explosion don't all behave the same way. Some have half-lives measured in minutes or hours, meaning they decay quickly and pose an intense but short-lived danger. Others remain hazardous for years, decades, or centuries. The most problematic are those with intermediate half-lives, long enough to persist in the environment, but short enough to be actively decaying and releasing energy. Iodine-131, for instance, has a half-life of about 8 days. It's readily absorbed by the thyroid gland, making it particularly dangerous to children, whose developing bodies are more susceptible to radiation damage. Cesium-137 has a half-life of 30 years and tends to accumulate in muscle tissue. Strontium-90, with a half-life of 29 years, mimics calcium and gets incorporated into bones. Each isotope tells its own story of how radiation moves through biological systems. The immediate area around our blast site becomes what's politely called an exclusion zone, though that term doesn't quite capture the strangeness of the landscape it describes. It's not that the area is empty, it's that it's empty of humans. Plants continue to grow, though they may show signs of radiation damage, stunted growth, unusual coloration, or genetic mutations that would be fascinating to biologists if they weren't so troubling in context. Animals that remain in the exclusion zone face increased cancer rates and reproductive problems, but many species prove surprisingly resilient. The absence of human activity can actually benefit wildlife populations, creating an accidental nature preserve where radiation is the price of admission. It's a dark irony that some ecosystems might actually thrive in areas too contaminated for human habitation. But the effects extend far beyond the immediate blast area. Radioactive particles travel on air currents, following wind patterns that can carry contamination hundreds or thousands of miles from the source. Areas directly downwind from our explosion receive higher concentrations of fallout, creating a pattern that resembles a teardrop stretching across the continent. Agricultural areas within this fallout zone face particular challenges. Crops absorb radioactive isotopes from contaminated soil, concentrating them in edible parts of plants. Livestock grazing on contaminated pastures accumulate radioactive material in their meat and milk. The food web becomes a pathway for radiation to reach human populations far from the original blast site. Modern radiation monitoring would detect the contamination quickly, leading to quarantines on food production and advisories against consuming locally grown products. But enforcement would be challenging across the vast, sparsely populated regions of the Amazon basin. Remote communities might consume contaminated food for weeks or months before authorities could reach them with warnings and alternative food supplies. The health effects of radiation exposure follow a grim but well-understood progression. High doses received quickly cause acute radiation syndrome, a condition that can be fatal within weeks. Lower doses received over longer periods increase cancer rates, particularly leukemia and thyroid cancer. Children are more vulnerable than adults, and developing fetuses are most vulnerable of all. From a public health perspective, managing the aftermath would require an enormous international effort. Medical facilities would need to be established to monitor and treat radiation exposure. Agricultural systems would need to be rebuilt in uncontaminated areas. Entire populations might need to be relocated, at least temporarily. The psychological effects might be as significant as the physical ones. Radiation is invisible and unpredictable, making it particularly frightening to human psychology. People living in contaminated areas would face constant uncertainty about their health and safety. The stress of wondering whether every headache or unusual fatigue might be a sign of radiation sickness would take its own toll on mental health. But time, as always, would be a healer of sorts. Radioactive isotopes decay according to mathematical laws that don't care about human convenience, but are at least predictable. Each half-life period reduces the intensity of radiation by half. After 10 half-lives, less than 0.1% of the original radioactive material remains. For isotopes like cesium-137, this means that severely contaminated areas would become merely moderately contaminated in about 300 years. That's a long time by human standards, but quite brief by geological measures. The Amazon rainforest has existed in various forms for millions of years. It has survived ice ages, droughts, floods, and massive climate shifts. Our hypothetical contamination, severe as it might be, would be just another challenge for the forest's remarkable capacity for adaptation and recovery. Interestingly, some of the most contaminated areas might eventually become valuable research sites for studying how ecosystems adapt to radioactive environments. Scientists studying the aftermath of the Chernobyl accident have made fascinating discoveries about how plants and animals evolve in response to chronic low-level radiation exposure. Our hypothetical Amazon exclusion zone might become an outdoor laboratory for understanding the long-term interactions between radiation and tropical ecosystems. And so, Gradually, life would find ways to continue. Cleanup efforts would reduce contamination in critical areas. Natural decay would slowly reduce radiation levels. New forests would grow, new animals would adapt, and eventually, humans might return to areas that were once uninhabitable. The landscape would carry invisible scars for generations, but it would endure, as landscapes have always endured the temporary catastrophes that mark the passage of geological time. The Earth's atmosphere, it turns out, is quite sensitive to sudden changes in its chemistry. While our explosion and its immediate consequences unfold at ground level, something equally significant is happening in the air above us. The slow development of what scientists call nuclear winter, though in this case it might be more accurately described as a global fever followed by an extended chill. Nuclear winter isn't actually winter in the traditional sense. It's more like throwing a light blanket over the entire planet, reducing the amount of sunlight that reaches the surface while simultaneously warming the upper atmosphere. This happens because the smoke and particles from our fires absorb solar radiation that would normally reach the ground, converting it to heat in the stratosphere instead. The physics involved is surprisingly straightforward. Smoke particles act like tiny dark umbrellas, absorbing visible light and re-radiating it as heat. When you have enough smoke particles spread across a large enough area, they can measurably reduce the amount of sunlight reaching the Earth's surface. It's the same principle that makes a city hazy on a smoky day, just scaled up to continental proportions. But the atmosphere is a complex system where small changes can have large consequences. The smoke from our fires doesn't just float passively in the air. It interacts with existing weather patterns, cloud formation, and the circulation systems that distribute heat around the globe. What starts as a local phenomenon gradually becomes a global one, as atmospheric currents carry the smoke particles across continents and oceans. The cooling effect might reduce global average temperatures by 2 to 3 degrees Celsius for several years. That might not sound like much, but it's enough to significantly affect growing seasons in agricultural regions around the world. Crops that depend on specific temperature ranges for optimal growth would face stress even in areas completely unaffected by radiation or direct fire damage. Interestingly, different regions would experience different effects. Areas closer to the equator might see relatively mild cooling, while higher latitudes could experience much more dramatic temperature drops. This uneven cooling would affect weather patterns, potentially shifting the paths of storms and monsoons in ways that could persist for years after the initial event. The reduced sunlight would also affect photosynthesis on a global scale. Plants around the world would find themselves operating with less solar energy, leading to reduced growth rates and potentially lower crop yields. Forests already stressed by drought or disease might face additional challenges from reduced light availability. The ocean's phytoplankton, microscopic plants that form the base of marine food webs, would also be affected by the reduced sunlight penetrating the water's surface. From an ecological perspective, nuclear winter represents a sudden shift in one of the most fundamental environmental variables, the amount of energy available from the sun. Ecosystems are finely tuned to existing light levels and seasonal patterns. A sudden, sustained reduction in available sunlight would force rapid adaptations or, in some cases, local extinctions. But climate systems are remarkably complex, and not all the effects would be straightforward cooling. The same particles that block sunlight also affect cloud formation, potentially increasing cloud cover in some regions while decreasing it in others. Clouds themselves have complex effects on climate, sometimes cooling the surface by reflecting sunlight back to space, sometimes warming it by trapping heat radiated from the ground. Ocean currents, driven in part by temperature differences between different regions, might also shift in response to the changed heating patterns. The Gulf Stream, the circulation system that keeps Europe warmer than it would otherwise be, depends on specific temperature gradients in the Atlantic Ocean. Disrupting these gradients could have consequences far from the original blast site, potentially affecting weather patterns across an entire hemisphere. The atmospheric chemistry would also be affected in subtle but important ways. The smoke particles would eventually be removed from the atmosphere by precipitation and gravitational settling, but while they're present, they would participate in complex chemical reactions with other atmospheric gases. This could affect the formation and distribution of ozone, influence acid rain patterns, and alter the atmospheric chemistry that affects air quality in regions around the world. Weather forecasting would become much more challenging during this period, as existing climate models would need to account for the unprecedented atmospheric conditions. Farmers, already dealing with potential radioactive contamination in some areas, would also face uncertainty about temperature and precipitation patterns. Emergency management agencies would struggle to predict and prepare for weather events that don't follow historical patterns. Yet, for all its global reach, nuclear winter would be temporary. The atmosphere has powerful self-cleaning mechanisms. Rain gradually washes particles out of the air. Atmospheric circulation systems disperse and dilute concentrations of smoke. Natural chemical processes break down complex particles into simpler compounds that are less effective at blocking sunlight. Most climate models suggest that the worst effects of nuclear winter would last for perhaps 2 to 3 years, with gradual recovery over the following decade. That's a significant disruption by human standards, long enough to affect multiple growing seasons and force adaptations in agricultural practices worldwide. But it's brief by geological standards, barely a moment in the Earth's long climate history. The planet has experienced similar or more severe climate disruptions many times in the past. Massive volcanic eruptions have injected far more material into the atmosphere, causing climate effects that lasted for years or decades. Asteroid impacts have created much more dramatic and long-lasting climate changes. Our hypothetical nuclear winter would be notable, but not unprecedented in the context of Earth's climate history. Perhaps most remarkably, life would adapt. During previous climate disruptions, some species have gone extinct, while others have thrived in the changed conditions. Evolution operates on timescales much longer than a few years of climate disruption, but ecological adaptations, behavioral changes, and migrations can happen much more quickly. And so the atmosphere would slowly clear, particle by particle, rain by rain, until the sky returned to its normal blue and the sun shone down with its accustomed warmth on a world that had learned, once again, that even the most stable-seeming systems can change more quickly than we expect. Recovery, it turns out, is often more interesting than destruction, though it takes much longer to notice. While the dramatic effects of our explosion unfold over hours and days, the recovery process stretches across decades and centuries, a slow, patient transformation that gradually reclaims a damaged landscape and rebuilds the complex systems that make life possible. The first signs of recovery appear surprisingly quickly. Within weeks of our hypothetical explosion, the first green shoots begin appearing in areas touched by radiation, but not completely sterilized. Plants have been dealing with natural background radiation for millions of years, and many species possess repair mechanisms that allow them to survive levels of contamination that would be lethal to animals. These pioneer plants aren't necessarily the same species that grew in the forest before. Radiation damage tends to affect complex, slow-growing organisms more severely than simple, fast-reproducing ones. The first plants to colonize the contaminated areas are likely to be grasses, ferns, and other species that can grow quickly and reproduce rapidly, allowing natural selection to weed out individuals too sensitive to radiation while favoring those with natural resistance. Bacteria and fungi, being even simpler and more rapidly reproducing than plants, adapt most quickly of all. Some bacterial species actually thrive in radioactive environments, using the energy from radioactive decay to power their metabolism. These extremophile organisms gradually break down radioactive isotopes, incorporating them into biological processes that render them less harmful to other forms of life. The exclusion zone around our blast site becomes, in effect, a vast natural laboratory where evolution operates under conditions unlike anywhere else on Earth. Scientists studying the aftermath would likely discover new adaptations, new species, and new ecological relationships emerging from the intersection of radiation exposure and natural selection. It's a dark form of innovation, but innovation nonetheless. Animal life returns more slowly than plant life, but it does return. Small mammals like rodents, with their rapid reproduction rates and adaptable diets, are often among the first to recolonize contaminated areas. They may carry radioactive isotopes in their tissues and face increased cancer rates, but their populations can sustain higher levels of mortality while still maintaining viable breeding groups. Birds, being mobile and able to fly away if conditions become too harsh, serve as living barometers of recovery. Their return to the exclusion zone would mark important milestones in the healing process. First comes scavenging species that can tolerate higher radiation levels, followed gradually by more sensitive species as contamination levels decline through natural decay. Large mammals take much longer to return, not just because they're more sensitive to radiation, but because they require extensive territories and complex food webs to sustain viable populations. The return of apex predators like jaguars would represent the final stages of ecosystem recovery, indicating that the entire food web has recovered enough complexity to support large carnivores. Human recovery would follow a different timeline entirely. Unlike plants and animals, humans can't simply evolve resistance to radiation over a few generations. Instead, human reoccupation of contaminated areas depends on technological solutions, decontamination efforts, medical monitoring, and careful management of exposure risks. Some areas might be decontaminated through intensive soil replacement, vegetation removal, and surface cleaning. This process is expensive and labor-intensive, typically reserved for economically or culturally important locations. Vast areas of Amazon rainforest would likely be left to recover naturally, with human activities restricted until radiation levels declined to acceptable levels. The psychological recovery process would be as important as the physical one. Communities displaced by our hypothetical explosion would face the trauma of losing their homes, their livelihoods, and their connection to specific places. Some might never return, choosing instead to build new lives in uncontaminated areas. Others might wait decades for the chance to come home, maintaining cultural traditions and community connections across years of exile. Agricultural recovery would require particularly careful planning. Soil contaminated with long-lived isotopes like cesium-137 would remain unsuitable for food production for decades. But certain crops might be grown safely in contaminated areas. Trees for timber, plants for biofuel production, or crops intended for non-food industrial uses. These activities could provide economic opportunities for returning communities while contributing to landscape recovery. Scientists studying the recovery process would make discoveries relevant to many other environmental challenges. Techniques developed for cleaning up radioactive contamination might prove useful for dealing with other forms of pollution. Species that evolve resistance to radiation might provide insights into cancer research or the development of radiation-resistant crops for space exploration. The economics of recovery would be staggering but manageable on a global scale. Previous nuclear accidents have shown that while cleanup costs are enormous, they represent only small fractions of global economic output. International cooperation would be essential, both for funding recovery efforts and for sharing scientific knowledge about decontamination and ecosystem restoration. Climate change would actually assist some aspects of recovery. As global temperatures rise, the growing season in areas affected by nuclear winter would gradually return to normal or even become longer than before. Shifting precipitation patterns might bring more rainfall to areas where forests are trying to regenerate, accelerating the natural recovery process. Indigenous communities with traditional knowledge of forest management would play crucial roles in recovery planning. Their understanding of native plant species, ecological relationships, and sustainable land use practices would be invaluable for designing restoration efforts that work with natural processes rather than against them. Perhaps most remarkably, the recovered landscape might eventually become more biodiverse than the original forest. Ecological disturbances often create opportunities for new species to establish themselves and for existing species to adapt and diversify. The patchwork of different recovery stages across the affected area would create a variety of microhabitats supporting different plant and animal communities. And so, gradually, the forest would return, not the same forest that existed before, but a new forest shaped by its unique history. Trees would grow again where the fireball once blazed. Rivers would run clear again through valleys once choked with ash, and life, in its endless creativity and resilience, would find new ways to flourish in a landscape forever changed, but not forever broken. 15,000 weapons, it turns out, might not be humanity's final answer to the question of destructive power. What if, in some alternative timeline, our species decided to take nuclear weapons to their absolute logical conclusion? What if we mined every scrap of uranium from the Earth's crust and transformed it all into weapons? The numbers become so large they start to feel abstract, but the physics remains stubbornly concrete. Current estimates suggest there are about 35 million tons of uranium scattered throughout the Earth's crust. That's enough fissile material to power human civilization for over 2,000 years if we use it for energy. But in our thought experiment, we're considering a different use, transforming all of it into weapons with a combined yield equivalent to 10 billion Hiroshima bombs. 10 billion is one of those numbers that slides past comprehension without leaving much of an impression. It's roughly the number of stars in our galaxy or the number of years since the Earth formed, expressed in millennia. But when we're talking about nuclear weapons, 10 billion means something specific. Enough explosive power to match the asteroid impact that ended the age of the dinosaurs 65 million years ago, except concentrated into a much smaller space and delivered all at once. The uranium cube representing this much destructive power would be roughly 3 kilometers on each side, a solid block of fissile material that would be intensely radioactive long before it was detonated. Building such a device would be impossible with any existing technology, not just because of the engineering challenges, but because the material would achieve critical mass and explode long before it could be assembled into a cube. But this is a thought experiment, so let's imagine we could somehow construct this impossible device and transport it to our same location in the Amazon rainforest. The warehouse that held our previous arsenal would now need to be replaced with something much larger, perhaps a structure the size of a small mountain, containing energies that would dwarf anything previously unleashed on Earth's surface. The physics of such an explosion would push beyond anything that existing models could accurately predict. Current understanding of nuclear weapon effects is based on devices thousands of times smaller than our hypothetical mega-weapon. Scaling up by such enormous factors means entering territory where the normal approximations and simplifications used in physics calculations might no longer apply. What we can say with confidence is that the explosion would be visible from space, not just as a bright flash, but as a sustained source of light that would temporarily outshine the sun as seen from Earth's surface. The fireball would grow large enough to be seen from neighboring continents, a new dawn appearing in the wrong direction and at the wrong time of day. The immediate crater would measure approximately 100 kilometers across, carving a wound in the Earth's crust deeper than many mountain ranges. For comparison, the crater left by the asteroid that killed the dinosaurs is roughly 150 kilometers across, but that impact had the benefit of cosmic velocities to achieve its destructive power. Our explosion would create comparable devastation through pure energy release. The environmental consequences would be qualitatively different from our smaller explosion. Instead of affecting South America primarily, this event would have global impacts that would be immediate and obvious to anyone on the planet. The mushroom cloud would probably reach into the mesosphere, the atmospheric layer where meteors normally burn up, creating a bridge of superheated material connecting the Earth's surface to near space. The blast would launch so much material into the atmosphere that day would turn to night across much of the globe. Unlike the gradual cooling of nuclear winter, this would be an immediate and dramatic change in lighting conditions. Noon would look like twilight, and actual night would be darker than anything experienced in modern human history. But perhaps the most significant difference would be in the scale of material ejected from the crater itself. Our smaller explosion vaporized trees and soil. This explosion would vaporize bedrock on the scale of entire mountain ranges. Thousands of tons of rock would be accelerated to escape velocity, leaving Earth entirely and becoming permanent additions to the population of asteroids orbiting the Sun. Most of the ejected material would fall back to Earth as a global rain of superheated debris. This isn't the relatively gentle fallout of radioactive particles we discussed earlier, but actual rocks and molten material falling from the sky at high velocity. The kinetic energy of this debris would heat the atmosphere to temperatures capable of igniting fires spontaneously across the entire globe. The resulting worldwide conflagration would consume virtually all surface vegetation within a matter of hours or days. Forests, grasslands, crops, and even individual trees in urban areas would ignite simultaneously, creating firestorms that would make our Amazon fires look like scattered campfires. The amount of smoke and ash generated would be orders of magnitude greater than our previous scenario. This global fire would consume vast quantities of oxygen from the atmosphere while releasing enormous amounts of carbon dioxide, fundamentally altering the atmospheric chemistry that supports life. The smoke would be so dense and persistent that surface temperatures would drop to near freezing levels across the entire planet, creating a worldwide winter that could last for decades. Under these conditions, photosynthesis would essentially cease. Plants around the globe would die from a combination of fire damage, cold temperatures, and lack of sunlight. With the base of virtually all food webs eliminated, most animal species would face extinction within months or years of the initial explosion. Human civilization would not survive such an event. Even communities in deep bunkers or nuclear submarines would eventually exhaust their food supplies and emerge to find a planet where crops could not grow and breathable air had become scarce. The few human survivors would face a world without functioning ecosystems, without agriculture, and without the technological infrastructure necessary to maintain modern life. And yet, from the planet's perspective, even this would be temporary. The Earth has survived worse, though not recently enough for anyone to remember. Our hypothetical mega-explosion would certainly qualify as one of the worst days in human history, but in the context of planetary history, it would be more like a particularly severe bout of indigestion than a terminal illness. The planet has weathered cosmic catastrophes that make our nuclear arsenal look like firecrackers, and it has always recovered, though not always in ways that would have pleased the species living at the time. The explosion of 10 billion Hiroshima bombs would release energy equivalent to that infamous asteroid impact 65 million years ago, but there are important differences in how that energy would be delivered. The dinosaur-killing asteroid brought its energy from space, arriving with the velocity accumulated over millions of miles of freefall toward Earth. Our explosion originates at the surface, which means the energy propagates outward in different ways and affects different parts of the Earth system. The most immediate consequence would be the creation of a crater of unprecedented size in human experience. 100 kilometers across and perhaps 20 kilometers deep, it would remove a small mountain's worth of material from the Earth's crust, temporarily exposing geological layers that haven't seen daylight for millions of years. The shockwaves from the explosion would propagate through the solid Earth like ripples through water, causing earthquakes that would be felt on every continent. These seismic waves would be strong enough to trigger volcanic eruptions around the globe as the shock waves disturb magma chambers that were already close to eruption. The ring of fire around the Pacific Ocean would light up with dozens of simultaneously erupting volcanoes, adding their own contributions of ash and sulfur dioxide to an atmosphere already choked with smoke from worldwide fires. The combination of our explosion and the triggered volcanic activity would pump truly enormous quantities of particles into the stratosphere. Unlike the relatively modest amounts of material from our 15,000 weapon scenario, this would be enough particulate matter to block sunlight on a scale comparable to the largest volcanic eruptions in Earth's history. Surface temperatures would plummet not by a few degrees, but by tens of degrees, creating ice age conditions that could persist for decades. But the most devastating consequence wouldn't be the cold or even the fires, but the disruption of the global food web. The darkness and cold would kill most plant life within the first year. Without plants, herbivorous animals would starve. Without herbivores, carnivores would follow. Ocean ecosystems would collapse as phytoplankton. The microscopic plants that form the base of marine food webs died from lack of sunlight penetrating the darkened atmosphere. Within a few years, the only surviving organisms would be those that don't depend directly on sunlight. Deep-sea communities around hydrothermal vents, cave ecosystems, and certain bacteria that derive energy from chemical processes rather than photosynthesis. The surface of the Earth would become a frozen wasteland, dotted with the preserved remains of forests and cities, a planetary museum of what complex life looked like before the explosion. Human extinction would be virtually certain under these conditions. Even the most elaborate underground bunkers would eventually exhaust their food supplies, and the surface world they emerged into would be incapable of supporting agriculture or any other form of food production. The few survivors might persist for months or years by scavenging preserved food and burning furniture for warmth, but without functioning ecosystems to provide renewable resources, even the most resourceful communities would eventually succumb to starvation or cold. The International Space Station and any other humans in orbit at the time would have perhaps the best short-term survival prospects, but they would face their own challenges. The explosion would likely destroy ground-based communication and navigation systems, leaving orbital crews isolated and unable to coordinate rescue efforts. More significantly, the spray of debris launched into space by the explosion could damage or destroy orbital installations, ending their inhabitants' chances of long-term survival. Yet, for all its devastating effects on complex life, our explosion would barely scratch the planet itself. The Earth is a large object, and even our enormous explosion would affect only a tiny fraction of its mass. The crater, massive as it would seem to any hypothetical human observers, would represent less than 1,000th of 1% of the Earth's volume. The energy released, enormous by human standards, would be a tiny fraction of the energy the Earth receives from the Sun each day. From a geological perspective, the main effects would be the creation of a new crater, some seismic activity, and the deposition of a thin layer of unusual material around the globe. Future geologists studying rock formations would find a distinct boundary layer marking the time of our explosion. A mixture of radioactive isotopes, rare earth metals, and synthetic materials that clearly indicated the former presence of an industrial civilization. The atmospheric effects, dramatic as they would be for surface life, would also be temporary on geological timescales. The particles blocking sunlight would gradually settle out of the atmosphere over a period of years or decades. Natural processes would begin scrubbing carbon dioxide and other gases from the air. Within a few centuries, atmospheric composition would return to something resembling pre-explosion conditions. Ocean chemistry would take longer to recover, as the sudden input of carbon dioxide from burning vegetation would acidify seawater and disrupt marine ecosystems. But even this would be temporary. The oceans have absorbed and neutralized much larger quantities of acid during previous mass extinction events, and they would do so again given enough time. The most persistent effects would be biological rather than physical. The mass extinction caused by our explosion would eliminate most existing species, but it would also create opportunities for rapid evolution among the survivors. Previous mass extinctions have typically been followed by periods of rapid diversification, as surviving species adapt to fill ecological niches left vacant by extinct species. And so the planet would endure, as it has endured ice ages and asteroid impacts and massive volcanic eruptions. Battered but not broken, temporarily simplified but still capable of complexity. In the aftermath of absolute catastrophe, time becomes the only healer, though it works very slowly. Following our hypothetical mega-explosion, the Earth would enter a period unlike anything in human experience, a planetary convalescence measured not in years or decades, but in millions of years, as life gradually rebuilds itself from the few surviving fragments scattered in deep places and hidden corners. The first million years would be the loneliest. Across vast continents covered in ice and ash, nothing would move except wind and the occasional rockfall. The silence would be profound, broken only by the sounds of geological processes, the grinding of ice sheets, the settling of debris, the distant rumble of volcanic activity slowly returning to normal levels. It would be a world without bird songs, without the rustle of leaves, without any of the countless small sounds that indicate the presence of life. But life, it turns out, is remarkably persistent. In the deepest parts of the ocean, around hydrothermal vents where superheated water bubbles up from the Earth's interior, communities of bacteria and primitive animals would continue their ancient routines, largely unaware that the surface world had ended. These deep-sea ecosystems operate independently of sunlight, deriving their energy from chemical reactions involving sulfur and methane. They would serve as arcs, preserving genetic diversity through the long darkness. Cave systems around the world would harbor their own survivors, bacteria, fungi, and perhaps a few small animals that had been living underground when the explosion occurred. These communities would be isolated from each other, scattered across continents like islands in a frozen sea, but they would maintain the basic genetic toolkit necessary for life to eventually recolonize the surface. As the atmosphere gradually cleared and sunlight began to reach the surface again, the first signs of recovery would appear in the most unexpected places. Bacteria capable of photosynthesis would begin growing in shallow pools of meltwater, creating thin films of green life that would be invisible from any distance, but would represent the first tentative steps toward rebuilding complex ecosystems. The process would be extraordinarily slow by human standards. It might take hundreds of thousands of years for the first simple multicellular organisms to evolve from these bacterial communities. Millions more years would pass before anything resembling plants or animals appeared on land. The recovery would follow patterns similar to the early evolution of life on Earth, but compressed into a shorter time frame because the basic genetic information for complex life forms would still exist in the surviving communities. Evolution in this post-catastrophe world would take unusual directions. Without the competitive pressure from established ecosystems, surviving species would be free to experiment with new forms and functions. Species that had been confined to narrow ecological niches before the explosion might diversify rapidly, adapting to the empty landscapes and filling multiple ecological roles. The planet's geography would also be different. The massive crater from our explosion would gradually fill with water, creating a new sea in the heart of what was once South America. This body of water would have unusual chemistry due to the radioactive materials incorporated into its sediments, potentially supporting unique forms of life adapted to high radiation levels. Climate patterns would slowly stabilize as the atmosphere cleared and normal solar heating resumed. But the distribution of land and water would be changed by the explosion and its aftermath, leading to new weather patterns and ocean currents. Ice sheets that formed during the nuclear winter would reshape coastlines as they advanced and retreated, carving new valleys and leaving behind new landscapes. The recovery of complex life would follow predictable stages. First, simple photosynthetic organisms would establish themselves in shallow waters and moist areas on land. These would gradually evolve into more complex plants, beginning the process of rebuilding terrestrial ecosystems. Early animals would likely be small and simple, feeding on the bacteria and primitive plants while slowly diversifying into new ecological niches. Forests would be among the last ecosystems to recover fully. Trees are complex organisms that require stable climate conditions and rich soils to thrive. It might take tens of millions of years for anything resembling the Amazon rainforest to develop again, and when it did, it would consist of entirely different species adapted to the post-catastrophe world. Marine ecosystems would recover more quickly than terrestrial ones, in part because the oceans would retain more biological diversity through the catastrophe. Simple algae would begin photosynthesis as soon as sunlight penetrated the water again, providing food for small animals that had survived in deep water refuges. These communities would gradually expand upward and outward, recolonizing the entire ocean system. The fossil record would preserve evidence of this recovery process, creating a unique geological signature that would be obvious to any future scientists studying Earth's history. They would find a sharp boundary between rock layers rich in fossil diversity and a zone containing almost no fossils, followed by layers showing the gradual return of life in new forms. Radioactive isotopes from our explosion would serve as time markers, allowing precise dating of the recovery process. Elements like cesium and strontium would be incorporated into the skeletons and shells of recovering organisms, creating a permanent record of when different species reappeared and how they spread across the planet. The recovering biosphere would have one crucial advantage over the original evolution of life. It would be starting with an atmosphere already rich in oxygen. This would allow complex organisms to evolve more quickly than they did during Earth's early history, when oxygen levels were much lower. What took billions of years originally might be accomplished in merely millions of years during the recovery. And so, very slowly, the planet would come alive again. Not the same life that existed before, but new life, different life, life shaped by its passage through catastrophe and adapted to a world with its own unique history. It would be a quieter world for a very long time, with fewer species and simpler ecosystems, but it would be recognizably alive, growing, changing, evolving toward complexity once again. Imagine being a geologist millions of years from now, carefully splitting rocks and finding the story we left behind. What would they make of the strange layer of rock that marks our hypothetical explosion? How would they interpret the sudden appearance of synthetic materials, radioactive isotopes, and the compressed remains of an entire technological civilization mixed with debris from a blast that temporarily rivaled the power of stars? The geological record is remarkably good at preserving stories, though it tells them in a language that requires careful interpretation. Rock layers accumulate slowly over time, each one capturing a snapshot of environmental conditions when it was formed. Most of these snapshots are quite ordinary. Sand deposited by ancient rivers, mud that settled on prehistoric ocean floors, volcanic ash from eruptions that happened millions of years ago. But occasionally, geologists find layers that tell more dramatic stories. The boundary between the Cretaceous and Paleogene periods, for instance, contains unusually high concentrations of iridium, an element that's rare on Earth but common in asteroids. This chemical signature, found worldwide, provides evidence for the asteroid impact that ended the age of dinosaurs. Our hypothetical explosion would leave a similar signature, but one that would be even more puzzling to future scientists. The first thing they would notice is the layer's global distribution. Unlike volcanic eruptions or asteroid impacts, which leave debris patterns that point back to specific locations, our explosion would leave a layer containing materials that clearly originated from all over the Earth. Rare Earth elements from electronic devices manufactured in Asia would be mixed with concrete from North American cities and steel from European factories, all melted together and scattered across the globe. The isotopic signatures would be particularly mysterious. Our explosion would create artificial isotopes that don't occur naturally, elements with specific atomic weights that could only be produced in nuclear reactors or weapons. Future geologists would find uranium-235 in concentrations far higher than anything found in natural uranium ore, along with plutonium-239, which doesn't exist in nature at all. But perhaps most puzzling would be the presence of synthetic materials that are entirely artificial. Plastics, synthetic fibers, and complex alloys that represent clear evidence of industrial activity. These materials would be concentrated in the blast layer, along with more conventional geological debris, suggesting that whatever created the layer had also destroyed a technologically advanced civilization. The spatial distribution of this debris would tell its own story. The highest concentrations would be found in a roughly circular pattern centered on what was once the Amazon basin, with decreasing concentrations at greater distances. But the global spread would indicate that the event affected the entire planet, not just the region where it originated. Carbon isotope ratios would provide additional clues about the timing and nature of the catastrophe. The massive fires following our explosion would burn vegetation worldwide, releasing enormous quantities of carbon dioxide with specific isotopic signatures. This carbon spike would be visible in rock formations worldwide, marking the exact moment when the planet's carbon cycle was dramatically disrupted. Future paleontologists studying fossil remains would find clear evidence of a mass extinction event coinciding with the unusual geological layer. Below the layer, they would find diverse fossil assemblages representing complex ecosystems. Above it, almost nothing for thousands or millions of years, followed by the gradual reappearance of life in new forms. The extinction pattern would be different from previous mass extinctions, showing the sudden disappearance of virtually all large organisms across all environments. The recovery pattern would also be unusual. Previous mass extinctions typically affect marine and terrestrial organisms differently, and recovery usually begins in one environment before spreading to others. Our explosion would affect all environments simultaneously and severely, leading to a more synchronized but also more delayed recovery process. Microscopic analysis of the debris layer would reveal additional mysteries. The presence of synthetic diamonds created by the extreme pressures of the explosion would be mixed with natural diamonds brought up from deep in the Earth's crust. Glass beads formed by the melting and rapid cooling of surface materials would contain inclusions of artificial materials unknown in the natural world. The radioactive signature would be the most conclusive evidence of the layer's artificial origin. While natural uranium deposits exist throughout the Earth's crust, they contain uranium-235 and uranium-238 in consistent ratios that reflect the natural decay processes that have been operating for billions of years. Our explosion would leave uranium with dramatically altered isotope ratios, clear evidence of artificial enrichment and nuclear processing. Even more significantly, the presence of elements like americium and curium, which have very short half-lives and don't occur naturally, would provide unmistakable evidence that the debris layer was created by nuclear technology. These elements could only exist in detectable quantities if they had been recently created in nuclear reactors and then distributed globally by some catastrophic event. Future scientists might initially struggle to explain how a single event could simultaneously destroy a global technological civilization and leave geological evidence of nuclear technology. The scale of the devastation would seem incompatible with any natural disaster, while the artificial nature of the debris would rule out external causes like asteroid impacts or massive volcanic eruptions. Eventually, they would likely conclude that some form of intelligent life had developed nuclear technology and then used it in a way that destroyed their own civilization. The global nature of the debris would suggest that this civilization had achieved worldwide distribution before its self-destruction, indicating a level of technological and social development comparable to modern humanity. The scientific papers written about this discovery would probably use careful, understated language to describe what must have been the most catastrophic self-inflicted disaster in the planet's history. They might refer to it as an anthropogenic mass extinction event or a technological catastrophe of global scope, academic terms that would barely hint at the drama of what actually occurred. And in their conclusions, these future scientists might wonder whether such events are common in the universe, whether technological civilizations inevitably discover the power to destroy themselves, and whether intelligence and wisdom always develop at the same pace. The Earth, as it turns out, has no particular attachment to any specific arrangement of life, including us. In the millions of years following our hypothetical mega-explosion, the planet would continue its ancient routines, spinning on its axis, orbiting the Sun, gradually cooling its interior, and slowly rearranging its surface through the patient processes of plate tectonics. From the planet's perspective, the explosion would be nothing more than a brief interruption in the long, slow dance of geological time. This is perhaps the most humbling aspect of our thought experiment, the recognition that even our most devastating weapons, deployed all at once, would represent only a temporary inconvenience to the Earth itself. We might end human civilization, collapse global ecosystems, and trigger a mass extinction that erases most complex life. but we would barely scratch the planet that hosts us. The Earth has been practicing resilience for over 4 billion years. It has survived the impact that created the Moon, bombardments by asteroids and comets, ice ages that covered continents with glaciers kilometers thick, and volcanic eruptions that released more energy than our entire nuclear arsenal. Each time, life has recovered, often emerging in new forms better adapted to the changed conditions. Our explosion would simply be the latest entry in this long history of catastrophe and recovery. Future geologists might classify it as another mass extinction event, comparable to the one that ended the dinosaurs or the even more severe extinction at the end of the Permian period, which eliminated over 90% of all species. But in the context of deep time, it would be just another chapter in the ongoing story of life's relationship with its planetary host. The recovery process would follow patterns established over hundreds of millions of years of evolution. Simple organisms would appear first, gradually building the chemical foundations necessary for more complex life. Photosynthesis would resume, slowly rebuilding the oxygen-rich atmosphere that enables large, active organisms. Food webs would develop from the bottom up, starting with bacteria and algae, progressing through simple animals, and eventually supporting complex ecosystems. But the recovered Earth would be different from the one that existed before our explosion. Evolution is not a process that moves toward predetermined goals. It's a process of adaptation to existing conditions. The post-explosion world would have different climate patterns, different geography, and different chemical conditions, leading evolution down paths that might never have been explored in our absence. Some of these changes might actually benefit the development of complex life. The temporary simplification of ecosystems could reduce competition and allow for more rapid evolutionary experimentation. Species that survived the catastrophe would find themselves in a world with abundant opportunities for diversification, potentially leading to the development of entirely new types of organisms. The Earth's recovering biosphere might develop capabilities that never existed in the pre-explosion world. Plants that evolved in environments contaminated with radioactive materials might develop enhanced DNA repair mechanisms that make them more resistant to cosmic radiation. Animals that evolved during the long nuclear winter might be better adapted to low-light conditions than any previous species. Over millions of years, these adaptations could lead to forms of life that are more resilient than anything that existed before the catastrophe. The selection pressure imposed by our explosion might ultimately result in a biosphere that's better equipped to survive future catastrophes, whether natural or artificial. The absence of humans would also affect the trajectory of evolution in subtle but significant ways. Human activities have influenced evolutionary pressures for thousands of years, selectively breeding crops and livestock, introducing species to new environments, and creating artificial selection pressures through hunting and habitat modification. Without human influence, evolution would be free to explore possibilities that might never have emerged in our presence. Perhaps most significantly, the recovering Earth would be free from the ongoing environmental pressures associated with industrial civilization, pollution, habitat destruction, climate change, and the extraction of resources for human use. This could allow for the development of more stable, long-term sustainable ecosystems than those that existed during the human era. Future intelligent species, if they evolved, would inherit a planet with a very different history from the one humans experienced. They would find evidence of our existence in the geological record, but they would also inherit the biological legacy of the recovery process. The species they evolved from would be the survivors and descendants of our catastrophe, shaped by evolutionary pressures that no previous life on Earth had experienced. These future intelligence might develop very different relationships with technology and the environment. Having evolved on a planet that bears permanent scars from technological catastrophe, they might be more cautious about developing potentially destructive technologies. Or they might be more resilient and adaptable, having evolved from lineages that survived the ultimate environmental disaster. The chemical and isotopic signatures left by our explosion would serve as a permanent warning embedded in the planet's geological memory. Future scientists would be able to study the exact conditions that led to the collapse of human civilization, providing them with detailed knowledge about the consequences of nuclear warfare. This information might influence their own technological development in ways that prevent similar catastrophes. In this sense, our hypothetical destruction might ultimately serve a constructive purpose, providing future intelligence with clear evidence about the dangers of certain technological paths while demonstrating the planet's capacity for recovery. The Earth would serve as its own museum, preserving the story of human rise and fall for any intelligence capable of reading the geological record. And so the planet would continue, patient and persistent, hosting whatever forms of life evolution produces while maintaining the physical and chemical conditions that make complexity possible. Our explosion would become part of its history, but not its conclusion. One more experiment in the long laboratory of deep time, one more test of life's remarkable ability to adapt, survive, and eventually thrive again. There's something almost merciful about the way the universe handles our mistakes. It simply waits for time to make them irrelevant. Our hypothetical nuclear catastrophe, devastating as it would be for humanity and current ecosystems, would eventually be absorbed into the Earth's long story like a drop of ink spreading through an ocean, gradually becoming so diluted that it's barely detectable. This process of cosmic forgetting operates on multiple timescales, each one offering its own form of healing. The most radioactive isotopes decay within years or decades, their dangerous energy dissipating into harmless heat. The intermediate-lived isotopes gradually fade over centuries and millennia. Even the longest-lived artificial materials we could create would become undetectable within millions of years, overwhelmed by the background noise of natural geological processes. The atmosphere, so dramatically altered by our explosion, would slowly return to familiar patterns. Carbon dioxide levels, elevated by the burning of global vegetation, would gradually decline as new plant growth absorbed the excess gas. The complex chemistry of atmospheric circulation would wash the air clean, particle by particle, rain by rain, until future beings would breathe air indistinguishable from what existed before humans ever walked the earth. Ocean chemistry would follow a similar path of recovery. The sudden input of carbon dioxide would acidify seawater and disrupt marine ecosystems, but the oceans have buffered against much larger chemical changes in the past. Natural weathering processes would gradually neutralize the excess acid, while new coral reefs and shell-forming organisms would slowly rebuild the calcium carbonate structures that store carbon and provide habitat for marine life. Perhaps most remarkably, even the massive crater from our explosion would eventually disappear. Erosion would slowly wear down its rim while sediments gradually filled its interior. Plant growth would stabilize the soil, and geological processes would continue reshaping the landscape according to the same laws that have operated for billions of years. Within a few million years, only careful geological analysis would reveal that anything unusual had ever happened in that location. The biological recovery would be the most creative aspect of this healing process. Evolution doesn't simply restore what was lost. It explores new possibilities, often discovering solutions that are more elegant or resilient than the original arrangements. The mass extinction caused by our explosion would create evolutionary opportunities that might never have existed otherwise, leading to forms of life that could be genuinely superior to what came before. Species that evolved in the aftermath might have enhanced resistance to radiation, better DNA repair mechanisms, more efficient metabolisms, or improved abilities to survive in challenging environments. Having passed through the filter of extreme catastrophe, the surviving lineages might be fundamentally more robust than their predecessors. The recovery process might also lead to greater biological diversity than existed before the catastrophe. Empty ecological niches would provide opportunities for rapid speciation as surviving organisms adapted to fill roles previously occupied by extinct species. Islands that lost their native species might be recolonized by organisms that evolved entirely different approaches to island living. Over geological timescales, the Earth might even benefit from the temporary simplification of its ecosystems. Complex natural systems sometimes become locked into suboptimal arrangements that persist simply because they're stable. A major disruption can reset these systems, allowing them to reorganize in ways that might be more efficient or more sustainable. Climate systems would also have opportunities to reorganize during the recovery period. The disruption of existing weather patterns might allow new circulation systems to develop, potentially creating more stable or more favorable climate conditions in some regions. The temporary absence of human industrial activity would give natural climate regulation systems a chance to re-establish themselves without interference. Future ecosystems might develop better natural mechanisms for carbon storage, more efficient nutrient cycling, or improved resilience to natural climate variations. The selection pressures imposed by our catastrophe could favor organisms that are better at maintaining environmental stability, leading to more self-regulating ecosystems. The planet's surface would also have opportunities for improvement during the recovery period. Without human mining, logging, and construction activities, natural processes would gradually heal the scars left by industrial civilization. Eroded landscapes would be rebuilt by vegetation and geological processes. Contaminated areas would be cleaned by bacterial action and natural chemical processes. Water systems would slowly purify themselves as natural filtration and dilution processes removed the contamination left by human activities. Rivers would carve new channels through landscapes no longer constrained by human infrastructure. Groundwater systems would gradually flush out pollutants that had accumulated over centuries of industrial activity. Even the recovering atmosphere might be cleaner than what existed during the industrial era. Without ongoing emissions from human sources, natural processes would gradually remove the accumulated pollutants from centuries of burning fossil fuels. Future beings might breathe air that's actually purer than what humans knew during most of recorded history. The silence of the post-catastrophe world would also represent a form of healing. The constant noise of human civilization traffic, industry, aircraft, machinery would cease entirely, leaving only natural sounds, wind, water, the calls of surviving animals, and the quiet processes of growth and decay. This acoustic simplicity might create conditions that favor the evolution of new forms of communication and sensing among future species. In this way, time would act as the ultimate healer, not by reversing the damage we caused, but by transforming it into something new and potentially better. The Earth would demonstrate its fundamental capacity for renewal, its ability to take even the worst catastrophe and eventually turn it into an opportunity for growth and improvement. The kindness of this process lies not in forgiving our mistakes, but in making them ultimately irrelevant. Future life would inherit a planet shaped by our passage, but not defined by it, free to explore evolutionary possibilities that we can't even imagine. Our greatest failure might become, in the longest view, just another step in the universe's patient exploration of what's possible. In the end, our thought experiment brings us face to face with a simple truth. Destruction is temporary, but creation is eternal. Even our most extreme scenario of nuclear devastation, catastrophic as it would be for human civilization and current life forms, would ultimately represent just one moment in the vast, ongoing experiment that is life on Earth. The universe's capacity for creating new forms of complexity and beauty appears to be inexhaustible, limited only by the laws of physics and the availability of time. This realization puts our nuclear capabilities into a broader perspective. Yes, we have accumulated enough destructive power to end human civilization and cause a mass extinction event. But we have not gained the power to end the story of life itself, or to prevent the emergence of new forms of intelligence and creativity on our planet. We are certainly capable of ending our own chapter, but we cannot close the book. Perhaps this is the most important lesson from our hypothetical journey, that while nuclear weapons represent an unprecedented threat to human civilization, they do not represent an existential threat to the planet or to the long-term future of life. The Earth has survived much worse catastrophes in the past, and would survive even our worst-case nuclear scenario. This doesn't make nuclear weapons less dangerous to us, but it does place their significance in cosmic context. The resilience we've discovered in our thought experiment emerges from the fundamental properties of complex systems. Life, ecosystems, and even planetary climate are not fragile arrangements that collapse at the first disturbance. They are robust, adaptive systems that have evolved over billions of years to survive and recover from catastrophes. This resilience is built into the basic physics and chemistry of how living systems work. Evolution itself is perhaps the most powerful force for recovery and renewal in the natural world. It operates not by maintaining existing arrangements, but by constantly generating new possibilities and testing them against environmental challenges. Even the most severe catastrophe simply becomes another selection pressure, favoring organisms and ecosystems that are better adapted to changed conditions. Our nuclear weapons, powerful as they are, work within these same natural laws. They cannot create energy, they can only release energy that already exists in atomic nuclei. They cannot destroy matter, they can only rearrange it. They cannot stop time, they can only create conditions that time will eventually heal. In the deepest sense, even our most destructive technologies are expressions of natural processes, subject to the same conservation laws and thermodynamic principles that govern everything else in the universe. This perspective doesn't diminish the moral importance of preventing nuclear warfare or the practical importance of managing nuclear weapons responsibly. Human suffering is real and significant, regardless of cosmic context. The loss of biodiversity, the collapse of ecosystems, and the potential end of human civilization would be genuine tragedies that deserve our utmost efforts to prevent. But understanding the broader context can help us maintain perspective when contemplating these risks. Nuclear weapons are not supernatural forces that transcend natural law. They are human technologies with specific, limited capabilities. They can cause immense damage within the human time frame, but they cannot fundamentally alter the cosmic processes that created us and that will continue long after we're gone. This cosmic perspective might even inform how we think about nuclear policy and disarmament. If our weapons truly threaten the existence of life on Earth, we might feel compelled to eliminate them immediately, regardless of other considerations. But knowing that their effects would be temporary on cosmic timescales might allow for more nuanced approaches that balance disarmament goals against other important objectives like international stability and security. The same perspective applies to other existential risks that humanity faces. Climate change, asteroid impacts, supervolcanic eruptions, and even potential artificial intelligence risks operate within natural limits and cosmic timescales that put their significance in context. While these challenges deserve serious attention and careful management, none of them represents a permanent end to the story of complexity and intelligence in the universe. Understanding this might help us approach risk management with appropriate seriousness, but without paralyzing despair. The universe has been creating increasingly complex and beautiful arrangements of matter and energy for billions of years, and this process appears to be robust against even severe temporary setbacks. Our role is to participate in this creative process while avoiding unnecessary catastrophes that would interrupt our own contribution to it. Future forms of intelligence, whether they evolve on Earth after our hypothetical catastrophe or emerge elsewhere in the universe, would face their own challenges and opportunities. They might develop technologies even more powerful than our nuclear weapons, or they might find ways to transcend the need for such destructive capabilities entirely. Either way, they would be participating in the same cosmic experiment in complexity and consciousness that includes us. Perhaps the most hopeful implication of our thought experiment is that intelligence and consciousness appear to be robust phenomena that can emerge from many different evolutionary pathways. Even if human intelligence were eliminated by nuclear catastrophe, the capacity for intelligence would remain in the universe, waiting to be expressed through different biological or perhaps technological forms. This doesn't make our own existence less precious or our own responsibilities less serious. We are the current carriers of consciousness and intelligence on our planet, and we have obligations to preserve and extend these remarkable phenomena. But it does suggest that these phenomena are larger and more durable than any particular biological form, including our own. As we drift towards sleep at the end of this long journey through nuclear hypotheticals, perhaps we can take some comfort in the universe's demonstrated capacity for renewal and creativity. Even our darkest scenarios lead eventually to new forms of light. Even our most catastrophic mistakes become, in time, opportunities for new kinds of wisdom. The stars continue to shine, time continues to flow, and somewhere in the vast cosmos, new forms of complexity and beauty are always emerging. Our nuclear weapons, fearsome as they are, represent just one small note in an infinite symphony of creation that has been playing for billions of years and will continue long after our particular melody fades away. Every piece of uranium we've imagined destroying the world could instead power it for thousands of years. There's a profound irony in our thought experiment. The same nuclear physics that enabled our hypothetical catastrophe also represents one of the most promising solutions to humanity's energy needs. The atom, it seems, offers us a choice between destruction and abundance, between ending civilization and powering it sustainably for millennia to come. Nuclear fission, the process that powers atomic weapons, is also the process that quietly generates electricity in power plants around the world. The difference lies not in the physics, but in the engineering. Weapons are designed to release their energy as quickly as possible, while power plants are designed to release the same energy slowly and controllably over years or decades. A single uranium pellet the size of a fingertip contains as much energy as a ton of coal. This isn't metaphorical, it's a direct consequence of Einstein's famous equation relating mass and energy. When uranium atoms split, they convert a tiny amount of matter directly into energy, achieving energy densities that chemical reactions simply cannot match. It's like comparing a firecracker to a lightning bolt. They both involve energy release, but they operate on completely different scales. But nuclear fission, impressive as it is, represents just the beginning of what's possible with nuclear technology. The same fusion reactions that power hydrogen bombs also power the sun and every other star in the universe. Fusion doesn't split heavy atoms apart. Instead, it forces light atoms together, converting hydrogen into helium while releasing enormous amounts of energy in the process. The Sun converts roughly 4 million tons of matter into pure energy every second through fusion reactions. This has been happening continuously for about 4.5 billion years, and there's enough hydrogen in the Sun to continue the process for another 5 billion years. It's the most successful energy generation system in our local neighborhood, and it operates without producing any radioactive waste or greenhouse gas emissions. Human efforts to harness fusion energy have been ongoing for decades, with researchers building increasingly sophisticated reactors that attempt to recreate stellar conditions on Earth. The challenge lies in containing matter at temperatures of hundreds of millions of degrees while maintaining the precise conditions necessary for fusion reactions to occur. It's like trying to hold a piece of the Sun in a magnetic bottle, which is essentially what fusion reactors do. The fuel for fusion reactions exists in virtually unlimited quantities. Heavy hydrogen, or deuterium, can be extracted from ordinary seawater. There's enough deuterium in the Earth's oceans to power human civilization at current energy consumption levels for millions of years. Unlike uranium, which must be mined from specific geological formations, deuterium is distributed evenly throughout the world's water supply. Fusion reactions produce helium as their primary byproduct, an inert gas that poses no environmental threat. While fusion reactors would produce some radioactive materials in their structural components due to neutron bombardment, these materials would become safe within decades, rather than the centuries or millennia required for fission waste to decay. It's energy production that's inherently clean and sustainable. The same physics that could devastate ecosystems in our thought experiment could instead eliminate the need for fossil fuels entirely. A world powered by fusion would produce no carbon dioxide emissions from energy generation, no acid rain from sulfur compounds, no particulate pollution from combustion. The environmental pressures driving climate change could be addressed not through reduction in energy use, but through a fundamental transformation in how energy is produced. Space exploration would be revolutionized by practical fusion technology. The enormous energy densities available from fusion could power spacecraft capable of reaching other star systems within human lifetimes. Instead of contemplating the destruction of our own planet, we might use the same nuclear physics to spread life and intelligence throughout the galaxy. Even our current fission technology, properly managed, could provide clean energy for centuries while fusion technology is being perfected. Modern reactor designs are inherently safer than older generations, with passive safety systems that shut down automatically if anything goes wrong. Advanced fuel cycles could extract much more energy from uranium while producing less radioactive waste that remains dangerous for shorter periods. The breeder reactor technology developed for weapons programs could be redirected toward energy production, creating reactors that produce more fuel than they consume. Such systems could extract 50 to 100 times more energy from uranium than current reactors, extending our fission fuel supplies for thousands of years while reducing the volume of radioactive waste. Perhaps most remarkably, the same enrichment technologies that create weapons-grade uranium could be used to create fuels for ultra-safe reactor designs that are physically incapable of melting down or exploding. These reactors could be small enough to power individual communities while being simple enough to operate safely anywhere in the world. The choice between destruction and creation with nuclear technology reflects a broader pattern in human technological development. Most powerful technologies can be used for either constructive or destructive purposes. Fire can burn down forests or power industrial civilization. Chemistry can create explosives or life-saving medicines. Information technology can enable surveillance states or global communication networks. What determines which path we take isn't the technology itself, but the wisdom with which we choose to deploy it. Nuclear physics doesn't inherently favor weapons over power plants. It simply provides enormous amounts of energy that can be channeled in either direction. The same scientific knowledge that enabled our hypothetical catastrophe could instead enable a future of energy abundance and environmental restoration. In this sense, our thought experiment serves not just as a warning about nuclear weapons, but as a reminder of the creative potential that lies dormant in our understanding of atomic physics. Every uranium atom that we imagine contributing to destruction could instead contribute to lighting cities, powering transportation, and enabling technologies we haven't yet imagined. The stars above us have been demonstrating fusion's potential for billions of years, patiently showing us what's possible when nuclear physics is harnessed for creation rather than destruction. Perhaps our next great adventure isn't learning to destroy worlds, but learning to power them with the same fundamental forces that make the universe shine. And so we arrive at the end of our gentle journey through one of humanity's more explosive hypothetical questions. We've watched imaginary fireballs bloom and fade, followed radioactive particles on their slow drift around the globe, and witnessed the patient process by which planets heal themselves from even the worst wounds we might inflict. What emerges from this thought experiment isn't just a catalogue of destruction, but a deeper appreciation for the remarkable resilience built into the natural world. Even our most powerful weapons, deployed all at once, would represent only a temporary interruption in the Earth's long, slow dance of creation and renewal. We might end our own story, but we cannot end the story itself. There's something both humbling and comforting in this realization. Our nuclear arsenals, fearsome as they are, work within natural laws that ultimately favor complexity and life over simplicity and death. Time, it turns out, is always on the side of healing, creativity, and new possibilities. Tonight, as you settle into sleep, perhaps you'll carry with you not the images of destruction we've explored, but the deeper truth that underlies them, that creation is stronger than destruction, that life is more persistent than death, and that the universe's capacity for beauty and wonder appears to be inexhaustible. If you found any peace in this strange exploration, feel free to follow us for more gentle journeys through science in the future. The cosmos is full of questions worth pondering, and there's always more wonder waiting to be discovered. Thanks for joining us here at Sleep Science. Sleep well.